I'd say we are going to start this soon. Yeah, so we are now live, I would say.
Okay.
Yeah, okay. So welcome everybody to this QPequi talk. Today we have the pleasure to have Davide Poderini with us. David is now affiliated with the Sapienza in Roma. Sorry if I mispronounced this. And we're going to talk about quantum causal influences today. Thank you so much, David, for being here with us. You're very
Good morning, everybody, and thanks to you for inviting me, for having this opportunity. And as you said, I'm from Sapienza University in Rome, and I'm mainly working on causal inference and its relationship with the classical causal inference and its relationship with quantum system in from an experimental point of view. And this talk today will be about an experimental demonstration of the incompatibility of quantum mechanics with some of the most basic classical causal inference constraints. So, but to get there, I will first start by introducing the causal inference framework for those of you that are not familiar with it. And especially I will show how the friction with quantum mechanics arise, and with some examples, and how we can use that to detect non-classicality, which is what we are interested in. Then I will show the scenario that we considered, which is one of the most simple scenario, where you have a causal structure of direct causation or common cause between two variables. And it's called the instrumental causal scenario. And then I will discuss the experimental demonstration of the result. So let me first start by saying that the causal modeling framework started to gain traction only, let's say, quite recently. I mean, it's I think 10 years or so in quantum information community, but it was developed a long time ago. And in this model formulation in particular, it was developed mainly by Judy Appel in the 90s, and in the context of artificial intelligence. And after that, it's found several applications in sciences, for example, in biology, medicine, econometrics, because it's a very general formal model to study the cause-effect relationship between events and to extract the information about this relationship from data. With this framework, what we can do is to falsify some causal assumption that we make on our system, and also infer causal relationship from data. But it was soon realized that the application of this framework to quantum system is far from trivial, and indeed, quantum systems seems to not respect causal constraints, and because apparently causal inference works differently for quantum systems, and this fact led to the realization that we should generalize causal model for quantum mechanics, and there are several theoretical works that tries to do that in quantum causal models. But what we can do is that we can also leverage this incompatibility to use it as a witness of non-classicality. And this is how conceptually, when we try to do this, we are trying to solve the opposite problem with respect of causal inference. In causal inference, we usually have some statistical data, and for example, we want to falsify a causal assumption that we made on a system. Here instead, what we are doing is that we are using the causal assumption, we are taking it for granted, and we use the statistical data to witness the non-classicality of the system. This means that, I mean, since the causal model is assumed, and we see from our statistical data that they do not fit in these constraints, then we conclude that we don't have a classical system, but we have a quantum system. That's the basic idea behind it. And this makes discuss. Yeah.
I have a question. How do you define the causal assumptions?
Yeah, I'm going to. I'm going to get there.
Okay.
I'm going to get there in a minute, like in 2 slides.
Sorry.
I will describe how exactly are defined. So this makes causal inference a very powerful tool in quantum physics. First of all, on one hand, we can it can help solve. It has a foundational interest, of course, because we are seeing the failure of this classical intuition of cause-effect relationship in quantum mechanics can help for searching for principles that define quantum correlation in non-local scenarios, for example. And I will also show how a Bell scenario can be interpreted in this way. And obviously this can give us some conditions and some constraints on the possible interpretation of quantum mechanics. But what I'm, at least from my line of work, most interested in is the application. And since whenever we have a possibility to witness non-classicality in a system, then we have we can leverage that to use it in quantum cryptography. So for example, for QKD distribution, for randomness generation, or for certification of quantum devices. And all of these protocols that we can, where we can leverage this possibility to detect non-classicality are very powerful, since they do not rely on the inner working of the devices. They are the so-called device-independent protocols. And so this is why this kind of study of the connection between causal inference and quantum mechanics can be very interesting, also from the application, from the applied point of view. So now I will describe a bit how we can define causal influence, but in this mathematical framework. And in this framework, any causal model is described by a directed graph. So the nodes of the graph represents a random variable. So every node is a random variable, which can stand, for example, can represent an outcome of one of our measurement in an experiment, in an experimental step. The arrows represents the causal relations, and obviously what we need is to avoid loop, to avoid situation when one variable can be causally connected to itself. So to avoid a return to the future like situation, let's say. What we have then is what is called a directed acyclic graph, or a DAG for short. Also, we can identify two different kind of nodes. One is represented by the observed variables. As I said, there are random variables that are the outcome of some measurements, and usually we consider them of fixed cardinality. At least for this presentation, I will. And then we can have an observed factor that we cannot observe or control, and they are called latent variables. And I will represent them by this triangle and with Greek letters. So when you have one of these DAGs, this directed acyclic graph, you have defined a structure that naturally implies a factorization of the joint probability of the whole distribution of the random variables, of the joint distribution of all the random variables involved. And this is called the generalized Markov condition. And what you have is that the distribution factorizes like this, where every variable is dependent only on the on its parent on the directed graph. Obviously, if you have a latent variable, then you need to marginalize on all possible values that it can take. And this kind of constraints. One of the important realization was to recognize that the Bell scenario is actually is nothing more than a particular instance of a causal model, and it's also one of the most obvious instances of this incompatibility between quantum mechanics and classical causal inference. So in this Bell scenario, I mean, we have these two distance parties, Alice and Bob, which can perform measurements on each of the part of a bipartite system, according to a pair of settings that here are called X and Y, which let's say they can take value 0 or 1. And also, we further assume that they are at sufficient distance so that the measurement, as well as the choice of the setting, can be to occur a space-like separated point. So, since in this case, relativity prohibits any influence between XA and BY, this causal structure is the appropriate one to describe this scenario, because as you can see, there are no causal errors from XA or YB. But we have just seen that this naturally implies a factorization on the joint probability, which now you can recognize to be the usual local causality condition, and that which directly implies the Bell inequality. So in this case, Bell inequality are nothing but constraint given by this causal assumption on our scenario. And as we know, this is violated by quantum mechanics. So we have to now conclude that either this kind of causal modeling does not work for quantum system, and that there are some our model, our causal model is falsified. So there are actually some communication between one part and the other. We have we need to put some more errors in this model, let's say. The beauty of this is that this does not add much, obviously, in the case of the usual best scenario. But the beauty of this is that you can generalize this approach very easily and to more complex and general cases. So which is very useful for complex networks, for complex quantum networks, for example. The recipe is all the same. You take a scenario, which is represented by a DAG. You write the Markov condition, the factorization, and then you try to obtain some inequality or equality constraint. And if there is some state, some quantum state that can violate some constraint when you substitute the latent variable with quantum resources, then this means that we can employ it to witness non-classicality, exactly like in the Bell scenario. But this all what I've said since now, it involves this factorization given by the Markov condition, but actually causal model can give you more information than just this factorization. And this is crucially what we are talking about in this experiment and in this particular case. So to exemplify this, I will show a very basic example taken from the Pearl book on causality, the one that I cited before from 2009. And where we have this very simple deterministic causal relationship between these three variables, x, y, and z, which, as you can see, they both gives mathematically the same condition, obviously, because even if they are reversed. And in particular, for the first one, we obtain y in terms of x, but obviously we can the mathematical relation, the equality relation does not imply a direction, so we can just have the same mathematical relation in the other model. And also we can find some relations which are not even directly connected to the situation, to the functional relationship that I saw, to the causal relationship that are shown in the figures. But assume now that I can fix y to some particular value. Then this it invalidates some of these relations, because, for example, now you cannot conclude anything in the first case for x given y, since I've imposed it to a certain values, while in the second situation you can. So it's definitely different. And the two other equations at the bottom of the page, they don't even make sense in this case. They're not true. What we are doing here is just the intuition behind what is called the intervention in causal models. So interventions, if you want, means that we are fixing the value of a variable in our causal model, and we are cutting all the incoming errors on that variable. This is formally expressed by the so-called do operation in the causal modeling framework. So do operation is just that. It forces one variable to take a specific value and erase all the causal influence, all the incoming causal influence on it. If you want, it's like a surgery on the diagrams, where we can study the diagrams by fixing some of the variables. And in this way is the only way to actually obtain information on the causal relationship in some cases, when it is much more stricter than the generalized Markov condition.
So would you say this is the main point of the Pearl theory on causality?
Yeah. I do.
Okay.
Yeah, I do. This whole graph approach, I mean, it makes sense when you do intervention.
Mm-hmm. Thank you.
And so let's now, in this talk, what I will focus on is one of the most fundamental causal problems in statistics. So what we have is that we have two correlated variables, A and B, and we would like to distinguish whether they are related by a direct cause or if there is a third latent variable that is causing this correlation. So in this case, as I told you, it's not possible to distinguish them by the measurement statistics alone. But to distinguish them, what we can use is the intervention. So as before, we intervene on A and we erase all causal influence. Now, using this do operation, we can define a quantity, which is called the average causal effect, that can quantify the causal influence between the two variables. As you can see, it's just the maximum of the difference of the B probabilities when I fix A to two different values, maximize over all the possible values and all the possible B outcomes. So it has a very intuitive meaning as a quantification of the causal influence between the two. But crucially, this makes sense only with the intervention and this do operation. So unfortunately, this quantity cannot always be observed. So a common example is pharmacological test. So
sorry, Davide. Just a quick question before I go forward. Is there a way to? So can you go back one slide?
Yeah, sure.
Is there a way to really compute, let's say, this quantity P, the probability of B given this do A from the joint probability distribution only, or is it impossible anyhow?
No, it's impossible. The joint probability,
right?
Yeah.
So
because this do operation, because this do operation represents, as I said, an intervention on
exactly.
I think it will be even more clearer when I'll show you the experimental apparatus that we do, because we are doing an intervention. And I mean, an intervention is a different experiment if you want.
Yeah, for sure. Yeah. Thank you. Sorry, just making this clear.
Okay. So as I said, a common example is the pharmacological tests. So we want to determine if the recovery of a patient is due to treatment, or maybe there is some common unknown factor that is influencing both treatment and recovery. It could be, I don't know. With treatment, we are formalizing the fact that the patient actually goes through treatment or does not. So this is also called the imperfect compliance. So there could be some latent factor that influences both the recovery and the treatment. For example, I don't know, a patient is more likely to not accept treatment when it has some bad side effects from the treatment, and these side effects maybe are correlated with the possibility of the recovery. Just one example. So in this case, intervention will mean to force all the patients to do treatment. And so in this case, obviously for ethical reason or just because it's infeasible, I mean, it's not a viable way. So to deal with these scenarios, there is
actually nowadays we can see this is not viable at all, right?
Yeah, exactly. It's quite relevant.
You cannot do it.
It's quite relevant now with the vaccine.
Interventions are not really easy, right?
Exactly. But fortunately, we have an alternative, and is the so-called instrumental technique. So the technique is to introduce another variable, which is called an instrumental variable. We'll call it X, which influences A, so influences the treatment, but it should be independent of the latent factor. So in this case, this variable would represent the fact that we are giving to the patient a medication or a placebo. So this is the base, the mathematical foundations, if you want, for the controlled pharmacological trial with the medication and placebo. And it can be shown that in this scenario, so when you also have this variable X, you can lower bound, you can lower bound the average causal effect, so this quantifier of causal effect by these quantities, which is expressed now on measurable distribution of A and B and X. Sorry, I did not explicitly say the notation. This is A, this is the value of B, and it's conditioned on the value of X. So now we can have some information, at least, even if not the value of the average causal effect. At least we have a lower bound using this method. But then there is also another problem. I said that X should be independent of lambda. So one could ask, when is my variable X, my instrumental variable X, a good instrumental variables? Well, fortunately, you also have some condition to check on that, and specifically, you have some inequality constraints, which are given as I explained before by the generalized Markov condition. So getting to this constraint is very similar to get from the local causality condition to Bell inequality. And these are the so-called Pearl's inequality. And then there is when the cardinality of X is greater than 2, then there are other condition called the Bonnet inequality. And these are the constraints that were first studied in a quantum context. So we can ask what happens to this scenario when I substitute the latent variable with a quantum state. So with, for example, for a quantum source. So when A and B are a measurement on a quantum state, and X is a setting. So for parent inequalities, there is no quantum violation. But we can show that for Bonnet's inequality, there is a quantum violation. So there is a quantum violation only when the cardinality of X is greater than 3. So this already shows that in this very basic scenario, you can already see some effects of the incompatibility between causal models and quantum mechanics. And this violation was tested experimentally in 2017 in our labs, and then has also been used, as I was saying before, for the ones that were already there, for applied to a certified quantum random number generator.
David, in this case, the cardinality of X would be the dimension of the Hilbert space or something like that?
No, because X is a setting, right? So it's just like the setting in a Bell scenario.
Okay, I see.
But yeah, if it would be, I mean, if it was A, then yes, it would be the
okay. So
the
A and
dimension
B
of the
are quantum systems, and X is just a classical thing.
A and B are quantum measurements on the row, which is a quantum system. While
okay, yeah.
While
Okay,
X is a setting.
Okay, thank you.
So, but then one can ask, what happens to the average causal effects and to this direct way of quantifying causal influence when we are dealing with quantum systems. So what happens when we are doing when we are doing an intervention? So first of all, how we define in this case the distribution and the do operation? Well, the quantum distribution is given by the Bond rule, obviously, where now M and N are, for example, P of M's that, as you can see here, they depend on the setting X, while the one on the subsystem B depends on the outcome of the measurement in A. And then to describe the do operation, what we're doing is just to avoid doing any measurement in A, so that we causally disconnect A from rho, and we fix the value of A in the measurement in B, and we have the usual Born rule just before with the reduced density matrix in B. And with this now we can easily define the quantum version of the average causal effect, the quantum A's, which is defined, which is just defined like this, just in the classical case with the do operation. And remarkably, also in this case, yeah.
Do you have any intuition about this expression on the do quantum operation? Because I would expect quite the opposite of that. Because identity is basically doing nothing, right? And in the classical case, you're basically setting your system to have some value, basically.
Yeah,
the thing is that kind of different.
Yeah, but the thing is that I'm setting the value of the outcome of A, so I'm not performing any measurement on A on the state row, on the part A of the state row. I'm not performing any measurement. I completely discard it. I ignore it completely, and that's what the identity operation means. And I fix the value of A here, which is the value that that goes to B. So it's the value, since they are still causally connected, this is the value that I fix that goes to B. So this is the meaning behind it.
Okay.
And so, as I said, even these values we can derive a lower bound for these values, and this was recently derived analytically in the case that we have an instrumental value. So just like before, an instrumental variable, sorry. So just like before, just like in the classical case, when we have an instrumental variable, so in this scenario on the left, we can bound the A's for the scenario on the right. And this is true also in the quantum case. The thing is that in the quantum case, as you can see, the bound is quite different. It's a bit more involved, but the thing is that, I mean, it's easily computable analytically, and we can find some situations like this. So there are some states and some measurements where we can have the classical average causal effect, the CAs written here, that is and it's lower bound that are bigger than the actual quantum average causal effect and in its lower bound. So apparently, analyzing the scenario classically overestimates the causal inference between the two variables A and B with respect to the quantum case. So this is a discrepancy, and so we can use it to detect non-classicality. And this is what we did, and it's what we did experimentally by implementing a version of this scenario. And to implement this scenario, we have to be careful of a basic thing. We need to have a experimental implementation that can do both the measurement in the instrumental scenario and the interventional scenario with the minimum possible disruption. Because it's true that, as I said before, we are actually performing a different experiment in the two cases. But we are also assuming that the causal influences in the other variables they stays the same. So what we want is a scheme that it can do both all in one, and so we need a feed-forward scheme to implement the influence of A in B, and a way to perform the intervention without disrupting and in any case modifying this feed-forward scheme. And what we did is that we are switching between, we are using a quantum random number generator and an optical switcher to switch between the two. And now I will describe in details how the experimental apparatus how the experimental apparatus works and what it's composed of. So yeah, as I said, we need that to assume that the other causal relationships are not changed where we're measuring in the instrumental instrumental scenario and in the interventional scenario. So we are our source of quantum state is characterized by a source of polarization entangled photon made with a nonlinear PPKTP crystal, which allows us to, which generates by spontaneous parametric down conversion of type 2, two photons of different polarization inside a Sagnac interferometer. This is a very common scheme and a reliable scheme to generate polarization entangled states. And in this case, we are aiming to generate this kind of state where the parameter alpha can be tuned by tuning the polarization of the pump laser that goes into the crystal. And then we have the two stations. So first we have the station in Alice, which just perform a standard polarization measurement, so with an alpha plate and a PBS. But crucially here, we have an optical switcher that is controlled by a quantum random number generator, which is a three-way optical switcher. So in this case, the quantum random generator with the first bit decides whether to perform an intervention run or an instrumental run, let's say a standard one. Well, the second bit, in the case that an intervention run is performed, fixes the values of A. So basically, every time we generate 2 bits in the quantum random number generator, we switch between one of these 3 fibers. The one below goes to a polarizing these splitters and performs the usual polarization measurement, while the other 2 they fix the value of A's. They fix the value of the measurement in A to the value 0 or 1. Then we have to send this information to the other side, to the Bob side, that also performs a polarization measurement. And we are doing this with by sending an electric signal to a Pockels cell, which is an electro-optic device that which is basically a piezoelectric material that change its birefringence with an application of a high voltage. But obviously, we also need to delay the photons that arrives in Bobs, so that it is the same couple, the photon is the same couple that is measured in A and triggers the Pockels cell in Bob's side. And we're using this electro-optic device because obviously we need very fast switching, and this device gives us a rise time of 90 nanoseconds, which is perfect for our needs. And so using this apparatus, we can realize both the scheme, right? Because when the quantum random number generator says to the optical switcher to do the first, the usual A measurement, what we are doing is basically the instrumental scenario, where the variable X is given by the quantum random number generator. When the quantum random number generator instead select the an intervention run, then we are completely ignoring the polarization of the photon in A, and we are sending the photon in one of the 2 detectors here on the right of the optical switcher, depending on a variable that is fixed by the QRMG. And we're doing this with a minimal disruption on all the other apparatus, because nothing changes. It's just the switch that electronically decides whether to do one or the other. So this is it's an operation that is doing locally on the Alice side. And so what we did is we generated states, as I said before, state polarization entangled state of this form, with varying the parameter alpha. And we performed the measurement using 2 different measurement settings. The first one, the measurement setting 1 that you can see on the plot on the left, is chosen to give the maximum possible discrepancy between the measured quantum average causal effect and the classical one. And as you can see here, the quantum violation remarkably is not maximal on the maximally entangled state, which is on the far right. And this is expected by the theoretical prediction, which is represented by the dashed curve. Well, in the other case, we chose different measurement settings to get a non-trivial bound on the quantum A's to see how well we could reproduce this bound experimentally. And as you can see, we did reproduce it quite with good accuracy, and we showed indeed that this bound, I mean, it can be useful even in experimental situation. So in conclusion, I show you how to use the causal incompatibility of causal inference with quantum mechanics. How can we turn that into a resource, and in particular, how this can generalize Bell locality and the device-independent protocols. And I show in particular how the non-classicality can be detected even in the simple case of the instrumental scenario. So the simplest case where we have two variables and we want to decide whether they have a direct cause or a common cause between them. The novel the novel part of this work and this approach is that we are using an intervention instead of just a constraint given from Markov rule. So we are using intervention to quantify causal influence, and as we can see, this is more powerful than the Markov condition, because we actually managed to detect non-classicality in the case where it would be impossible with the other approach, because in this case the x variable was of cardinality 2, and we said that in that case we only have pairs inequality that are not helpful because they are respected also by quantum systems. And so this kind of interventional schemes in general are quite unexplored for non-classicality weakness. And so we hope that this could be the start of a new way of looking at non-classicality in the causal framework. And maybe it could be useful as a building block for quantum protocols. Thank you for your attention.
Maybe it was not too long. For the great talk. No, that was perfect. Thank you so much. I would say we have time for a few questions. So do you have questions? I have a question. I'm gonna make it first then. So you have shown a lot of different measures in your plots, and it seems like there is a green one which works best. Can you tell anything about that? Yes, so you have this green one, which in both plots seems to be witnessing the quantum violation, let's say.
So the green ones are the experimentally measured values of the quantum average causal effect. So they are measured in the quantum case directly doing the intervention.
I see. And what is the difference between the blue and red one? So
yeah, sorry, I was unclear on that. So
no worries.
The red ones are the lower bound, the classical lower bound of the average causal effect. So is the bound on the classical average causal effect computed using our distribution with the formula that is valid for the classical in the classical case. So
I see
this formula here.
Yeah, I remember that you had a lot of lower bounds and stuff.
Yeah. Okay. So this formula here.
I see.
So this is valid in the classical case, and this C ace is LB. It's exactly that in the plot.
Yeah.
While the quantum version of it, so this one, which is what we measure directly, it's what we measure directly with our intervention scheme in our apparatus, and these are the green dots, the green triangles in the plot here. While the other one, the blue dots, are the lower bound, the quantum lower bound. So the lower bound corrected for the quantum case.
I see. And how is it device independent? Or it's not?
It's device, yeah. Well, it's device independent in the sense that we are only making causal assumption. So, if you are defining device independent only when you have, for example, space-like separation and loophole-free Bell inequality, then no other causal, very few other causal scenarios can be said to be device independent.
Mm-hmm.
But if you are saying that device independent means that you're only making causal assumption, then this is what we are doing here. We are only considering causal assumptions.
Okay, I see. Oh, that's really nice.
Yeah, this could be useful if you think about it, because, for example, in a cryptographic protocol, we do not necessarily always need the all-powerful Bell scenario. Maybe sometimes we have good reason to trust that our causal assumptions are true. Causal assumptions are very basic assumption anyway. So maybe I have good reason, for example, I don't know what A is doing, I don't know what B is doing, but I have good reason to know that they have this causal, that they respect this causal model. Because, for example, I have control on the signal from A to B, and I know that how that signal is working. So it's like you are giving more trust to something. You are giving something in return, like you can detect non-classicality in more cases, and you have a much easier experimental implementation. So it's a compromise. It's a compromise in this case for everyone.
Yeah. Okay. Is Emmanuel related to this stuff, to this project?
Emanuele, yeah.
Yeah, Emanuele, it is as well.
It is as well. Yeah, as you can see.
That's cool.
Maybe I passed too fast, but yeah, they're here. Iris is the.
I see. It is the first author. Yeah, Emanuele.
It's the first author,
nice.
And Emanuele also.
Rafael as well. Okay.
Yeah.
Yeah, nice. Send my regards to him and to Iris as well.
Yeah.
Okay, so I'd say we can have further questions if you have any. So if we don't have questions, I would say we can call it an end for today. So I thank you once again, David. This has been a really nice talk. I would say, even because this is the first actual experimental quantum information result we've got here in this series of talks. So, and actually, it's been really great to see you once again, and I expect to see you in person, in real life once again. Maybe even better if it happens in Natal, because it would be the perfect thing.
Yeah.
But anyway.
Yeah, I hope so.
Yeah. Let's see. Thank you so much. Do you want to say anything else?
Thanks to you. No, I just want to thank you again for this opportunity to let me.
Yeah, no. I mean, it's been great. Let's stay in touch, okay?
Okay.
Bye. So bye everybody.
Bye. Goodbye.